Welcome back, everybody. So we left off with the quote unquote the area under the curve discussion. So this is a big discussion that we need to have about what it means to be area. So if we know how the integral is to form, which we talked about before here, right? Right there, is that the definite integral is equal to the definite integral from A to B is equal to the limit as you make that Riemannian sum, right-handed, left-handed, midpoint, whatever you want to do, as you make those rectangles become infinitely smaller. And if we remember how that's formed by taking a fixed width for each rectangle, and then the height of each rectangle is dependent upon the function itself. So like that is your height. And that's fine and dandy if your function is above the x-axis. But as soon as your function starts going below the x-axis, the definition kind of starts to become a little bit wonky. So when you're dealing with a negative piece, like I have in red there, the heights of those rectangles are going to be negative, which will result in the rectangles having negative area, which doesn't make sense in a physical world. And so we have to be cognizant of that and tack on a negative sign to counteract that. So this is the thing that's important here. The definite integral can be positive and negative. The definite integral, so for example, just on this graph here right now, here is 5 and here is 9, right? Like you don't need to write this down, but the integral from 5 to 9 of f of x dx, the definite integral from 5 to 9 of f of x dx, that is going to be a negative number. If you plug that into your calculator, whatever it is, you will get a negative number. So if I ask you to compute that integral, your answer will be negative. But if I ask you for the area of that region, you tack on a negative sign to counterbalance it. Does that make sense? So the definite integral can be positive, it can be negative. Whereas if I'm talking about specifically area as a concept is intrinsically positive. We cannot have a thing having negative area. So this is where kind of the math and the real world have a little bit of a headbutt, and we have to recognize the shortcomings of our definition. So if I'm asking for just area, then we have to be cognizant of that. We have to tack on negative signs as needed. Whereas if we're just being asked to find the definite integrals can be positive and negative. So as I kind of explain in this little subsection here, if your function is less than 0, if you're below the x-axis, then the definite integral from a to b will be negative because it will represent negative area. Because what do you mean by the area under the curve if you're underneath the x-axis? Does that make sense? So in those situations, we just tack on a negative sign to take into account that we are dealing with heights that are quote unquote negative. That's how we handle that situation. So we're going to use definite integrals to represent the areas of the shaded regions that are given. So this is the integral, so the area under the curve y equals e to the x on the interval 1 to 2. That's that blue shaded region. So that region is above the x-axis, so the definite integral and the actual area coincide. So let's call this region R. Then the area of region R is going to be the integral from 1 to 2 of e to the x dx. And your calculator, by the way, has a formula. Like if you got the calculator, I recommend it has a formula for this. Or not a formula for it. It can compute definite integrals, which is pretty dope. Or dopamine, as the kids say, right? Is that what the kids say? I'm pretty sure. Whereas this one right here, y equals the square root of x minus 2. If you look at this curve is below the x-axis. So the actual integral from 0 to 4 of the square root of x minus 2 is going to be a negative number. So what I do I tack on a negative sign to fix that. The area of the region is going to equal negative the integral from 0 to 4 of square root of x minus 2 dx. Couple things here while we're talking about it. The bounds, the upper and lower limits of your integral are always dependent upon what the variable mentioned in the differential is. So the differential is that last thing, right? Dx. So that means that we're integrating with respect to x. So our values, like our bounds, need to be bounds in terms of x. Yes.
Don't you write the exact derivative?
Say what?
Don't you write the exact derivative?
Ah, we're gonna get there soon. Yeah, you're getting ahead of us. You're getting ahead of us. So that's this one. Now the this third one, there's two pieces to it, and it doesn't say it, but this is pi right here, and this is 2 pi. So we have region 1 and region 2. I guarantee you, if you plug into your calculator the integral from 0 to 2 pi of sine of x, you will get 0. Because it'll add up all of this area, and then it'll add up this area, and that'll be negative in its eyes, and it'll cancel each other out. But we're talking about the actual area of this shaded region, so we need to tack on a negative sign for that secondary piece. So this should be the area of the total is equal to the area of region 1 plus the area of region 2. Area of region 1 will be the integral from 0 to pi of sine of x dx. And the second one will be negative. Or you could just subtract it. However you want to do it is fine with me. But it's going to be minus the integral from pi to 2 pi of sine of x dx. Now, it is important for us to talk about what Dylan just mentioned because I already feel it. The question arising of, is this really how, like, going back to that previous problem, don't worry, I'm coming right back to this. But going back to this problem, is this really how we have to find area every time? Is this really the way we have to do it? We have to find a general summation, R sub n or L sub n or M sub n, and then from there we have to we have to then write it in terms purely of n by using all those formulas, and then from there we have to then take a limit, and then we finally get the answer. Is that the only way? Is that the only way? What if, like, this was all fine and dandy when we were doing polynomials, because like when you have the f of x plus axi, or a delta x, right? A plus delta x times I. What if your function is e to the x? Then f of a plus delta xi is equal to e to the a plus delta xi. And last time I checked, there's no summation formula for that. So, yet our calculus can do it. So there must be a faster way. And in fact, there is. And that's the good news. That's the good news. But we haven't gotten there yet. We will get there in 4.4. So we need to go through 4.3. And that, like, I promise you, there is a much, much faster way to compute these. But right now, we don't have that information. We don't have those capabilities. So we have to use other things. So one thing I want to mention here, or no, this is another one. Use the definite integral to represent the area of the following shaded region in blue of f of x equals negative x squared plus 4, negative 3 to 3. Now, you might already tell by looking at this graph where it switches over, right? It switches over at 2 and negative 2. That's like the dividing value, right? But why? Like, what we need to do is to find place, let's define X value where it switches, solve f of x equaling 0, right? If you want to know where it switches from being positive to negative, you need to find the zeros or the roots of the function, where it crosses the x-axis. And so negative x squared plus 4 equals 0. That gives me x equals plus or minus 2. Once again, this was a very, very quote unquote inherently clear one. Like you can even see it from the graph that 2 is where they cross. But what if this was a function that was not so nice? How would you know how to break it up? You need to find the places where it equals 0. So we have 3 regions, R1, R2, and R3. So the area of the total, the area of region 1 is below the x-axis from -3 to -2. So we have a negative sign in front, negative integral from -3 to -2 of negative x squared plus 4 dx, plus the integral from -2 to 2 of negative x squared plus 4 dx. That one is above the x-axis, so that definite integral will actually end up being the same as the area. And then the last one is below the x-axis, so we have to tack on a minus sign again and get that this is the, and then so minus the integral from 2 to 3 of negative x squared plus 4 dx. And later on, once we get to 4.4 and beyond, we'll be able to figure out what that is. Yes.
How do you know when to subtract your plus each other?
If it's below the x-axis, it's negative area, so you tack on a negative sign to take care of it.
That's it?
Yep. All right. That's why the first and this is like the first one is area of R1. This is A of R sub 1. This is A of R sub 2. And this is the area of R sub 3. You could write it as plus the negative, or you could just make it minus. Doesn't matter to me. I think this looks a little more official. Now, there's another thing about this, just as an aside, is you could use symmetry to solve this. Technically speaking, from 0 to 3, it's the same thing as from -3 to 0, the same area. So you could just double the area from 0 to 3 if you wanted to. That's fine too. However you want to do it though. So right now we have no way of solving these things. No way to do it. We don't know any quick tricks to solve these things other than by using geometry. So we can use geometry here. This one. Use geometry to evaluate the following definite integrals. The integral from 0 to 2 of the square root of 4 minus x squared. So the curve y equals the square root of 4 minus x squared. We got to remember what this means. The definite integral represents the area under the curve of the integrand, the thing on the inside. So the function that we're looking at, we're going to be trying to find the area under that curve. So does anybody know what that curve is? Y equals the square root of 4 minus x squared. We talked about it a long time ago in 2.5. Maybe if I squared it on both sides. And then maybe moved the x squared over. It's a circle. Circle with radius 2. But it's the upper half of the circle because it's the positive square root. The negative square root gives us the lower half of the circle. So upper half of a circle. So what this actually ends up looking like here's -2, here's 2, and here's 2. And your curve looks like this. And so we want this region. And so that's a half circle. We know the formula for the area of a circle. Pi r squared, right? Pi r not round, pi r squared, like pi r not squared, pi r round. Cornbread are square. It's a dumb joke. Yeah, so this will be 1/2 of a pi r squared, 1/2 of a pi times the radius, which is 2 squared. Actually, it's more than that. This is wrong. Why is this wrong? What did I shade wrong? Something's wrong with what I did. This wasn't the integral from -2 to 2. Yeah,
It's 0 to 2.
it's from 0 to 2. So it's only a quarter circle. Apologies. Area of a quarter circle. So it shouldn't be 1/2, it should be 1/4, which is just pi. So the area of that region is pi. Now, as I told you, by the way, a long time ago, this integral was actually on my calculus 2 exam. So I was on a quarter system, and so my second quarter of calculus dealt with purely integration. And you will learn a way to solve this in 182, but with all the information that we have in 181, even at the very, very end of this semester, like with all the material we'll learn on how to solve integrals, you will not be able to find this without knowing a thing called either trigonometric substitution or integration by parts, which are things you learn in 182. So I had to figure this out by geometric means during that exam, and I did not figure that out, so I got that one wrong. Yes.
The 1/4, that's the entire circle?
The 1/4 is the quarter of a circle. So the whole circle's area is pi r squared. So this is a quarter of it, so it's 1/4 of it.
Why would you do that?
Because that's the shaded region.
Okay.
This next one minus the absolute value of x. Does anybody know what that would be? What does that region look like? From -1 to 1. Does anyone remember? This requires us to go back to our knowledge of linear transformations. So anybody remembers that? So absolute value of x, that's the V shape, right? But that's negative absolute value of x, so it's the upside down V. And then it's negative absolute value of x plus 1. So it's a reflected absolute value function that's been shifted up 1 unit. So what it actually ends up looking like, it's like this. Here is one, here's 1, here's -1, here's 1, and we have a triangle. This is y equals 1 minus the absolute value of x. So we're talking about this region. And that's a triangle. And we know the area formula for a triangle. 1/2 the base times the height. Or you can even bust out that a times b times sine theta BS. You know, we can bust out that one if we really want to. But then you need to know what the angle is. And so I don't recommend that. But it's an area triangle with base 2. Nope. Area of a triangle with base 2 and height 1. So the area of this region, since it's above the x-axis, we don't need to tack on a negative sign. Well, I mean, we're going to be computing it by geometric terms anyways. We're not going to be using the formula at all. So this becomes 1/2 the base, which is 2, times the height, which is 1, which is just 1. Okay. So that's how you can use geometry to solve these problems without even integrating, without even finding, without even doing the things that we need to do. So the question then becomes, yeah, still.
This is, to figure out geometrically, not by the rectangular.
Yeah, not by that. Not yet. Now, there are some properties about the definite integral. Some of them very, very strange, other ones kind of intuitive. So this one, the integral from a to a. So if you're trying to find the integral from a to a of f of x dx, what do you think that's going to be? Let's think about it. Let's just draw a generic curve for a second. You don't need to draw this, but I want to like think about it. Here is a. And let's just say b is over here. If I wanted the integral from a to b, that would be the area under that region. But I'm doing the integral from a to a, which is just this line. What's the area of a line? 0. It's a line is a one-dimensional object. It doesn't have area. So the integral from a to a is exactly 0. So if you have the same number for the upper and lower bounds, then there's no width at all. So you have no rectangles. The integral from a to b, and I want to highlight, I meant to erase this. I need to make that change. I want this to be blue a and red b. The integral from blue a to red b of f of x dx, you can actually change the bounds of integration. You can flip them with each other. But when you do that, this becomes negative the integral from b to a.
Why would you do that?
Excellent question. Most of the time you don't. It's a very, very useful trick in certain aspects of mathematics. That's why we know it. It can be beneficial, like there are certain niche situations. What I like to realize what this means, by the way, and this will make way more sense once we get to 4.6 and 4.5, is that even if your integral, so we're gonna be doing things in 4.5 and 4.6 called integral substitutions, and that can sometimes change the bounds of integration. And so what this is telling us is it's okay to have an integral like this. You don't need to write this down once again, but it is okay for your integral to have a lower bound that is a bigger number. It is all right for that to happen. You will still be able to do everything like normal. You can switch the bounds and make it negative in front, but it's not necessary. You can still just compute it like this. I guess that's my main point, is that you can even if you have bad bounds that look weird, you can still integrate. Yes.
If you wanted to, you could.
Yeah.
If you wanted to, you could flip the number signs.
And just make this. You could reasonably just do this negative integral from 5 to 7 of f of x dx. You could do that. You're allowed to. So the point being, once we get to 180, once we get to integral substitution, you will do things that will change bounds of integration, and that's okay. That is okay. You can do that. It is allowed, and is not a problem.
Thank you.
The other one the constant multiple rule is that any constant, just like with differentiation, just like with limits, just like basically everything in mathematics, you can pull constants out. So this is the same thing as k times the integral from a to b of f of x dx. And that makes sense, right? You're trying to find the area under the curve k times f of x. What that's doing is that's just taking all the heights of f of x and multiplying them by k. So every height gets multiplied by k, which means that you can just find the area of f of x and then multiply that by k. That's what that's telling us geometrically. The next one, the integral of a sum or a difference. Yes, Dylan?
So cut the constant, which is k.
Yeah, constant. Like you can factor out a constant. The sum and difference rule basically says that you can break apart functions. This is the integral of from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And by the way, just as an aside that I meant to mention, that that dx at the end, you cannot skip it. You will get marked down if you don't write it. And I remember vividly when I was a TA, one of my students was really angry at me and went to my I was a TA and they went to the instructor of the course, who was actually in the office right next to me, and started cussing them out, saying, "I got the right answer. Why did I get marked down?" And like literally cussing at the professor. And the answer is because it's not mathematically valid. If you don't have a dx there, it's not a full sentence. It's not a full mathematical sentence. So don't forget the dx's. Don't forget the plus c's. Yes.
If I do the antiderivative before I place down the dx, would you still mark that down?
If the dx isn't there, I will mark down.
You won't mark.
Yeah. Otherwise you're claiming two things that are equal that aren't equal. The dx is important. It's more like, and this is going to serve as a very important thing later on in your mathematical career. If you decide to take 283, you will start having to take double integrals and triple integrals, where the order of what you'll see things like this. You'll see the integral from a to b and then c to d of f of x comma y dy dx, and the order matters. Which one goes first changes everything. If you do dy dx, your first inner bounds need to be in terms of y. If your second one is dx, your second integral needs to be in terms of x. If you flip it up, or if you forget it, you won't be integrating properly. That's the reason why I'm a big stickler on it, is to prepare you for 283. So it is important to write that dx. Don't just assume just like with limits, we had to write the limit every time, because otherwise it changes what it means. The other one is that, notice for this one, the integral from a to b, a to c of fx dx plus the integral from c to b of fx. Notice that the first integral stops at c and the second integral starts at c. You can actually combine these. So this is equal to the integral from a to b of f of x dx, regardless of what c is. So c could be a much larger number than a and b. It doesn't matter. The fact of the matter is that if they start, if the first one ends and the second one starts at the same number, you can combine them together. So as an example of this, the integral from -7 to 10 of f of x plus f of x dx plus the integral from 10 to 3 of f of x dx is equal to the integral from -7 to 3 of f of x dx.
That 10?
Yeah, it's 10 on both the top and the bottom of the second, the top of the first integral, bottom of the second integral. So even though it looks weird, right? This is an integral from 10 to 3. So like the bottom bound is larger. It does not matter. As long as they have the same number, you can combine them. Yes, Dylan?
Is it like they canceled each other out almost?
Mhm.
Or is it exactly what's happening?
That's exactly what's happening. They're canceling each other out. Basic, like we could go through a proof of it if we wanted to. I want to try and keep it light today and try and get us out early. So we can be on our merry way. I don't know if anybody has any other classes today. Hopefully not. Hopefully you just have this one and then you can head out. But if you want to see a proof of why that works, please feel free to ask. This one, if f of x is greater than 0 on the interval a to b, then the definite integral also is greater than 0. Yes.
Going back to the last question, if it was like a minus sign in the middle instead of a plus,
Then it would not work.
it would not work.
Nope. That is specifically if you're adding two things together. There are ways that you can manipulate these things to involve a minus sign, but that's neither here nor there. Like we'll deal with that later. So what this is telling us, part F, is saying that if your function is above the x-axis, you're dealing with positive areas. So of course, your area is going to be positive. As a consequence of this fact, if f of x is less than or equal to g of x on an interval, then the definite integral is less than the definite integral. So if that's true, then the definite integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. And that makes sense. If your function, if g is a larger function, that means that it's higher up on the y-axis, meaning the area that's present is larger. So to just to visualize this a little bit, here's g of x, and here's f of x, and here's a and b. G of x is this whole thing, whereas f of x is just the tiny part. So it's a much bigger area. The purple area is much bigger. So if your function is smaller than another function, then its definite integral will be smaller than the other one's definite integral. And then as a consequence, and the reason why this one's not useful for us per se, but it is useful in proving the fundamental theorem of calculus, which is why I have it up here, is that if your function is bounded, meaning it has a lower bound of lowercase m and an upper bound of capital M, then, well, from G, we have that the integral from a to b of lowercase m dx is less than or equal to the integral from a to b of f of x dx, which is less than or equal to the integral from a to b of capital M dx. Now we can even formalize this more. So, and I'm really trying to do this to give us an intuition about what the definite integral is. This one's really, really important for understanding this. I can actually write that this actually means that m times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to capital M times b minus a. This integral becomes this, and this integral becomes this. Why? Try to think about it geometrically. Right? What is the function y equals m for any number m? It's a constant, right? It's a constant function. It's a horizontal line. So what you've got, so again, here's A, here's B, and here is M. If this is our curve, then the area of the region is this. That has a height of lowercase m and a width and the width is equal to b minus a, right? B would be the entire distance, but we're subtracting off that little bit of extra from a. So that's why it's lowercase m times b minus a, because we're dealing with a constant function that's going to be a horizontal line. So the area under that curve is going to be a rectangle. And the area of a rectangle is length times width. The length or the height, or width times height. So the height is just the height of the function, m, and then the width is b minus a, because this whole distance would be b, but we're going to take off this little bit of a, so b minus a. That's the reason for that. That becomes very, very useful in the proof of the fundamental theorem of calculus, which is the only reason why I'm mentioning it. You're not going to be tested on that one at all. Other ones, maybe. But this is a very, very fun problem. Love this problem. Great problem. And I'll show you how I solved it. So, suppose f and g are functions such that the definite integral from 0 to 5 of f of x dx is 10. The definite integral from 5 to 7 is 3, and the definite integral from 0 to 5 of the g is 2. Find the following. The integral from 0 to 7. Okay. How do I solve this? Now, we're not given anything about the function, right? There's nothing we know. That might seem scary, but it's actually to our advantage. That means that we can just generalize this idea. We don't have to know what the function is to figure this out. So what I like to do is I like to draw a little number line and label all my my values. So I've got 0 for my x values. So I've got 0, I've got 5, I've got 7.
The x value on top, the upper limit.
Say it again.
The x value is the upper limit.
All the bounds, 0, 5, and 7. Okay. From the bounds of the integration. Now, we don't know what our function looks like. We don't know. It could be something completely ridiculous. It could be something else. So, because it doesn't matter, because that part is not given, it doesn't matter to the problem. So what we'll do is we'll just draw a generic calculus graph like this. This is our f of x. We don't know what it is, but this is what it is. It's just some function. Now, what we do know is we know, I'm going to highlight it in green, we know this piece. This is known. And then this piece here is also known. So, how would I find the integral from 0 to 7? I just take the integral from 0 to 5, that's the first chunk of it, and add the second chunk. So the integral from 0 to 7 would be the green chunk plus the red chunk. Does that make sense? And that has to do with understanding how the definite integral works. And that once again, I didn't draw a picture for the other one, the reason why this works. And I think the reason why E works. And I think that might help us a little bit understand. If I just draw a generic calculus graph, you don't need to worry about this. Here's A, here's B, and here's C. Here's my function, right? The integral from A to B is this whole thing. And then here is C, right? Please don't draw this here. We need space for everything else. If you're gonna draw it. So the integral from A to C. The integral from A to C is this little chunk. The integral from C to B is this little chunk. Adding them together gives you the whole integral from A to B. That's how that works. Yes.
2 plus 3.
So it'll be 10 plus 3. G of X is the integral from 0 to G's area is 2 from 0 to 5. So this becomes, just to write it down formally, the integral from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx, which is going to be 10 plus 3, which is 13. So the definite integral from 0 to 5 is the green piece, that's 10. The integral from 5 to 7, that's the second piece, which is 3. And then together, that's 13. So you can just draw a quintessential graph because we know a lot here. And we know a lot just by looking at that information. We don't need to know what the function looks like. Yes.
So this is, we're still drafting this geometrically, where we're using the given answers,
Yes.
and we're saying, okay, what is that?
That's correct.
And then from 0 to 7, because of 0 to 5. Oh, okay.
Good.
Yeah, I get it.
It's weird. It's weird at first. This next one, the integral from -5 to 0. -5 to 0. Sorry, from 5 to 0. The bounds are all weird. So you can just flip it using that property. This is the same thing as negative the integral from 0 to 5 of f of x dx. So that's going to be negative 10. Negative 10. Next one, the integral from 5 to 7 of 2f of x. That's a constant that's being affected to it. You can pull constants out front. So this is the same thing as 2 times the integral from 5 to 7 of f of x dx. And we know what the integral from 5 to 7 is. It's 3. It's given in red. It's underlined in red. So this is really just 2 times 3, which is 6. Last but not least, you can also, remember, you can split apart summations and differences. So we can split this apart and take care of the constants. This is the integral from 0 to 5 of f of x dx minus 4 times the integral from 0 to 5 of g of x dx. Integral from 0 to 5 of f of x, that's given in red, which, or not red, in green is 10, minus the integral from 4 times the integral from 0 to 5 of g of x, which was given. I didn't underline it, but it's 2. So that's 10 minus 8, which is 2. Right? Right. Like, wait to see the next one. The next one's even more fun. The next one's really, like, it's really testing your brain on how to figure out, like, it's one of those things, like, there's some really fun puzzles. Just fun math puzzles. That's what I like to think these are. These are just math puzzles. And so this one, given the information about the function h, find the following definite integrals. We know that the integral from -3 to 4 of h is 5. The integral from 0 to 4 is 2, and the integral from 0 to 6 is -3. We could, yeah, and we should. So let's go ahead. We'll make a generic one over here, but I decided to do this for each one separately, and I think that's probably the way I'd like to do it. So each time I'm going to draw a little line. What do we like? So here it is. Here's our little line, and knowing what the values we have -3, we have 0, we have 4, and we have 6. Right? Those are all the bounds that we know that were given the problem. -3, 4, 0, 4, 0, 6. That's what we have. And so our generic function h looks like this. This is h. And so what do we want? We want the -3 to 0 piece. There's no integral at the top that tells us -3 to 0. So this is the piece we want. Exactly. That's what's going to happen. So we know the integral from -3 to 4. We know that one. We also know the integral from 0 to 4 is this one. And right off the bat, I think I've got the answer. I could write also the 0 to 6, but it might actually end up muddying it. But it's not a problem to write it down. How do I find the green? Take the difference. The orange one has all of the area from -3 to 4. The red one only has the area from 0 to 4. So if I took off the area from 0 to 4, I'd just be left with the area from -3 to 0. Does that make sense? It's okay if it doesn't. Maybe actually visualizing it with an actual function. Here's -3, here's 0, here's 4. And this is just a generic calculus graph, right? We don't know what the function looks like, but we want this area right here. We know the area of the entire thing. And we know the area of, sorry, I should have made this in green, not pink. We want this piece. We know the orange and we know the red. You can also draw a big picture like this if it helps you visualize it better. Some people do it this way, but if you took the entire orange and subtracted off the red, you'd get the green, which is what we want. I think, like me personally, the small graph works, but that's my brain. Everyone's brain works differently, so whatever helps you doesn't matter to me. Does anyone want me to keep that up there? I can keep it up there. No. Just wanted to grab everything except for, there we go. Oop. So this is going to be the integral. The integral of the orange minus the red. So -3 to 4 of h of t dt minus the integral from 0 to 4 of h of t dt, which is 5 minus 2, which is 3. Part B is a little less bad because we just found it in part A. So integral from 0 to 4, already given. That's red. The integral from -3 to 0, we just found. So this was given info, and we found this in A. Found in part A. So this is going to be 2 minus 3, which is -1. It is okay for our definite integrals to give us negative values. The definite integral as a concept can be positive or negative. When you're talking about specifically area, which I'm not talking about here, I'm looking purely at these things as mathematical objects. Just like remember when we're solving a a Pythagorean theorem, right? We're trying to find the side lengths of a triangle, right? When we do that, we have a squared plus b squared equals c squared. You get when you solve for c or a or b, you get a plus or minus. But when we're talking about a triangle, you don't worry about the negative side length. That doesn't make any sense in the real world. So it's the same kind of idea of the fact that as a purely mathematical object, it can be positive or negative. We have to know the context to determine whether it's positive, whether we need to make it just positive or not. And that should be clear from the problem. If I ask for specifically area of a region, that's when you need to tack on them, like make the area positive. Okay, the integral from 4 to 6. All right. So let's draw another number line. -3, 0, 4, and 6. This is our curve, h of t. So we know, what do we want? We want the integral from 4 to 6. Okay. The integral from -3 to 4, I don't think is going to help me very much, right? You could draw it, it's fine. But what I do know is I do know the integral from 0 to 4. And I do know, and I'm going to underline in purple now, the integral from 0 to 6. And then I also know the integral, and I'll put it here for reference just to show that it's how would I find, and sometimes maybe putting the green below doesn't help you. I just do it to make sure I know that that's the thing I'm trying to find. But you can put it up above too. It looks like red plus green is equal to purple. So green is equal to purple minus red. Right? Does that make sense?
Yeah.
So it's going to be purple minus red. So this is equal to the integral from 0 to 6 of h of t dt minus the integral from 0 to 4 of h of t dt. And that's going to be, what did we say? -3 minus 2, which is -5. Now, I will say also, if you want to just, if your mind doesn't work well with these visual things, you can still just use the definitions to figure this thing out. I notice, and here's what I can do. I notice that they both have a 0 involved, right? They both have a bound of 0. What do we know about bounds? You can flip them, but by tacking on a negative sign. So you could write this, so 0 to 6 h of t dt, and you could rewrite this as plus the integral from 4 to 0 of h of t dt, and that will equal the integral from 4 to 6 of h of t dt. So what I'm doing here is I'm saying, okay, well, I can get 4 to 6 by just putting 0 as an option and then like combine the two together. That's not the way I would do it, but it is something that you can do if you want. Last but not least, upon saying that out loud, I realized that's not maybe that's not really that helpful. So don't worry about that. If it made sense to you, awesome. But you'd be the only one. This last one, the integral from -3 to 6. So -3, 0, 4, and 6. our generic graph that we're going to draw. And we want the whole kit and caboodle. We want -3 to 6. So what do we know? We know the integral from -3 to 4. We know the integral from 0 to 4. We know the integral from 0 to 6. Those are the ones that were given. Red, orange, and purple. Looking at those things, there's no way that I could add them up to get or subtract them in any way. I mean, yes, there is. Yes, there is. What would you do?
The orange subtract the purple.
So the orange subtract the purple would give us kind of an interesting area. Because we don't know, like the purple doesn't give us anything here. So if we subtracted them, we'd be able to cancel this area, but then we take this, if we were to subtract purple and orange together, we'd be able to cancel this area, but then we get the positive version of the orange and the negative version of the purple, which isn't exactly what we want.
What if the red fill up that?
So if we added that in, yes. So we can add the purple and the orange together, or sorry, the purple and the orange together, and then subtract off the red. Because none of that, like, because if we add the purple and the orange together, the purple plus the orange gives us the whole thing, but an extra amount from 0 to 4. That makes sense?
Yes.
So we just need to subtract off the red. That's one option. Option 1. Would be orange plus purple minus red. And that's because doubling up. So if we subtract off one red, we end up getting exactly what we want. We get the whole thing. That's one option. Now, the other option that I would notice is in C, we found the integral from 4 to 6. This was found in part C. So you could instead do orange plus pink. You could do the orange given plus, like you could do that. Option 2 is orange plus pink. Either way, it's going to get you the same answer. If you do option 1, you got the integral from -3 to 4 of h of t dt, plus the integral from 0 to 6 of h of t dt, minus the integral from 0 to 4 of h of t dt. That'll be 10 plus -2. Wait, 0 to 6. It's -3, not. And then minus 0 to 4, 2, which gives you 5. But yeah, and then option 2, you get the integral from -3 to 4 of h of t dt, plus the integral from 4 to 6 of h of t dt, which is going to equal 10 plus -5, which is what we found in part C, which also equals 5. Either way, it works out. You have a question? It's okay if you do.
So option 1.
The 10, 5. What am I doing? 5. I don't know why I wrote 10. Why did I write 10?
question.
I'm thinking of the previous one, aren't I? I'm thinking of the previous one. Okay. As a small aside, I was looking at my notes that I've written for this, and I was starting to panic because on my notes I got 0, and I was noticing that I was going to get 5. I was like, okay, maybe I just made a mistake on my notes. So it should be 0. Sorry about that. Either way, it's going to be 0. And that's okay, by the way. It can be the case that your integrals give you 0. They can be negative, they can be positive, they can be 0. It does not matter.
It can be a negative number. Right?
It can be. But if you're talking about it in terms of area, then it can't. If I ask you for the area of the shaded region, the definite integral gives you the negative version of it, so you tack on an extra negative to make it positive. Love these types of questions here, by the way, unless there's any other questions on these ones. There are many different, like, my favorite thing about this is that there is no one right answer. There is no one way to find it. There are multiple ways to go about doing it. We learned from the previous one, from part A, we learned the integral from -3 to 0, right? In part A, we learned this piece in light purple. So you could do light purple plus purple to do it as well. Light purple was 3. Purple is -3. 3 plus -3 is 0. Once again, another way to do it. So there was many different ways to go about solving this thing, which I think is very, very fun. It's always my favorite type of math problem is when there's not one right way to do something. Because it really gives you an insight into thinking of things differently. So this one here, and I think this is the last question, and then we'll call it a day. Sound good? Okay, so we're given the graph of f. And one thing I will mention, if this is ever a problem on a quiz or an exam or anything like that, I will tell you straight up that these problems, you can like it'll say in the problem statement. I didn't do it here because I wanted to save on space, but assume that all shapes are nice shapes. So I did my best to make sure that this shape looked like a perfect half circle, but every once in a while when you're graphing these things, because of scaling issues, it makes it look like it's not a half circle. It is a half circle here. That's a semicircle. The bottom portion is a triangle. The top portion is a triangle plus rectangle or a trapezoid, however you want to do it. So the integral from -7 to -3. That is this region. Right? Here's -7, here's -3. So that's the upper half of a circle with radius 1, 2, 2. Yeah, radius 2. 1/2 times pi times the radius squared, which is 2 pi then. Any questions on that? One half, once again, because it's only a half of a circle. It's a semicircle. Integral from -3 to 2. All right, I'm going to underline that in green. That's got to be this area, -3 to 2. Now, that's a triangle with base 5, right? Base equals 5, and then the height is from the tallest part, right? From the bottom part. So the height is 3. So it's going to be, John Doe student writes this, 1/2 the base times the height, and he gets 15 halves. Why is John Doe student wrong? John Doe student boxes in 15 halves and says that's the answer.
Is it because?
Remember, this is talking about a definite integral only. This isn't talking about the area. If it said the area of the green shaded region, then the answer would be 15 halves. But this is asking about the definite integral from -3 to 2. So this should be negative. Negative because below the x-axis. Definite integrals can be positive and negative and 0. Area has to be positive. So because this is a definite integral and not an area that we're looking at, we're going to keep the negative sign there. Just like when you're solving a quadratic equation in the real world, you sometimes get negative numbers. Like when you take the square root of both sides, you do the plus and the minus. And we just ignore the minus sign in a real world sense because that minus sign doesn't make any sense. But in a mathematical world, just purely mathematical, that minus sign is important. That's why it's 15 halves. All right. The integral from from 2 to 7. I'm doing purple. Notice that there's a 2 right there. So that can be factored out front. That is 2 times the integral from 2 to 7 of f of x dx. And that purple region is from 2 to 7. That's this region right here. Now, there's 2 ways we can go about it. Because that is either, you can think of it in 2 ways. You could think of it as a trapezoid. Does everyone remember the area of a trapezoid? Come on. Pop quiz. What's the area of a trapezoid?
1/2 times
1/2 times.
base times height.
Very close. It's the average of the bases times the height. So it's b1 plus b2 divided by 2 times the height.
Ah.
So this is base 1, this is base 2, this is the height. Now that would be one way to do it, but I don't expect anybody to remember the area of a trapezoid except for me.
How did rectangle and triangle?
Exactly right. That is exactly what I would do. I would break this down into a triangle. I'm gonna color code this with pink, I guess. Triangle plus a rectangle. Either way is fine though. The only time you're ever going to be asked to for the formula of a rectangle is if you see me in the street. I'll bump into you and say, "What's the area of a trapezoid?" Quick, at gunpoint, apparently. God. Of course, I am kidding. God, I don't even want to own it though. I don't even want to touch one. So the 2 is still out front. It's 1/2 the base, which is 2 times the height, which is also 2 for that triangle. The base is from 2 to 4, so that's a distance of 2. The height is 2, and that rectangle has a height of 2 and a width of 3. Plus 2 times 3. That's going to be 2 times 2 plus 6. That's 16. Any questions on those? Isn't this cool? Isn't it fun? Come on, it's fun. It's fun just like using little shapes to just figure out some areas. There like I know I've said several times during this class this semester that like this is my favorite topic or whatever, like this is some of my favorite stuff to talk about. But integration truly is one of my favorite things to talk about. It is so interesting, and there are so many cool tie-ins to everything we've learned. Integration takes everything that we've learned before. It takes limits, it takes derivatives. Even though we haven't seen the derivatives yet, we will see them soon. And it incorporates them. So it ties in everything. This is the start of what I consider to be true heavy mathematics, of thinking critically without just being told what to do. Soon we're going to be learning a thing that occurs, which is instead of just saying, here's the process, do the process, it's here's the problem, figure out what process to use, then do the process. Does that make sense? It's adding on an extra layer, which I think is just awesome. So this one right here, the integral from 7 to 5, bounds are all weird. Bounds are all weird. The bottom bound is larger than the upper bound. So what we're going to do is we're just going to flip it. So tack on a negative sign out front. And that is the area of the rectangular piece. From 5 to 7. I'm going to highlight that in orange, actually. Or no. What color haven't I used yet? I haven't used red. Okay. I just realized that that's not the integral from 4 to 7. 4 to 7, that's that whole rectangle. This is a smaller sub-rectangle. That's this rectangle. It's not even a rectangle, it's a square. That's negative 2 times 2, which is negative 4. They're just so I'm so excited, guys, because this is the time where I get to create so many ridiculous problems that are so theoretical and so annoying. And then my wife has to shoot down those problems and say, no, that's too hard.
Can you show me the graph again?
Yeah.
Sure. Put the square.
Right there. So,
It's 5 and 7.
yep, because that's what the integral was. It was the integral from 5 to 7. Last but not least, and then we will call it a day. So I've planned on I don't want to eat up any more people's holiday time with their families. So we're gonna do this last one very quick. Integral from 1 to 1 of f(x) dx. It's the same bound. Same number. So thinking about it geometrically, this is the area under the curve between 3 and 3. There's no area. It's a line. There's no width. So this is 0.
Oh, that's it. They can't show that.
Super quick for that last one. There's no area whatsoever because there's no width. In order to have area, you need to have 2 dimensions. Yes.
Would that be considered like just a line?
Yes.
0?
Yeah. So what it would look like is, technically speaking, I'm going to draw it in pink, even though I've used pink. From negative, what did I say? From 1 to 1.
Yeah.
That would be this line, and that's it. A line has no area. It's one dimensional. Area, it requires 2 dimensions in order to be something. And that is the end of 4.2. We'll start up next week with 4.3 to talk about the rest of everything and figure out the last little bits of material. Yes.
Where's the quiz?
The quiz is on Wednesday. And more details on that as we get closer to it. For now, you guys have a great rest of your day, a great holiday. I hope you guys enjoy many delicious foods, and good time with family, and a much well-deserved little mini break. I will caution you, just as an aside, try to enjoy it as much as possible And on like Saturday night, take a deep breath and and hold it in and know that we're going to go into the last part of the semester. We're going to the final lap of Mario Kart. You know how the music starts to go fast? It goes that one, it starts to go faster. That's exactly what happens every fall semester. We come back from Thanksgiving, and nobody's prepared. I don't want that to happen to you guys. So take a deep breath on Saturday and say, I'm ready to get back into the semester. We're gonna finish this bad boy out, or some other vulgarity, and we're gonna finish it. Okay, guys? Have a great day, have a great Thanksgiving, and I'll see you guys on Monday.